Now it is my pleasure to introduce our two presenters that we have for today. First, we'll have Dr. Augustine Pieri. Dr. Augustine Pieri obtained his BS in chemistry from the University of Southern California and his PhD in chemistry from the University of California, Santa Barbara. He has been an analyst in different sections of the laboratory and since 2007 has worked in the LC-MS department, developing all analytical methods by that technique. Prior to becoming technical director in July of 2016, he has been working as methods development manager for all departments of the laboratory. After Dr. Augustine Pieri presents, we'll have Mr. Craig Butt, who is the staff application scientist in the Environmental Food and Beverage Division of SciEx with over 20 years of mass spectrometry experience. While at SciEx, he has developed methods for targeted screening of pesticides in cannabis, non-targeted screenings of pesticides in fruits and vegetables, PFAS and water using high-resolution accurate mass spectrometry, and qualitative profiling of natural products. He obtained his PhD in environmental chemistry at the University of Toronto, where his thesis research investigated the fate of poly and perfluorinated organic compounds, PFAS, in biological systems. He was an NCERC postdoctoral research fellow in the Nicholas School of Environmental at Duke University and later became the research scientist in the department. So ladies and gentlemen, let's first welcome Dr. Augustine Pieri.
Thanks for the introduction and good morning or good afternoon to everybody tuning into the webinar. So my name is Augustine Pieri. I'm the technical director at Weck Laboratories, and today I'll be talking a little bit about a couple of methods we developed for the analysis of PFAS in certain food commodities to, hopefully answer the question of, are PFAS moving into the food chain? So I want to give a little bit of background on our lab first. We're a medium-sized, kind of full-service analytical lab. Primarily, we work in environmental samples, so things like drinking water, wastewater, surface water, that kind of stuff. But the list of analysis we do are actually pretty big. We do everything from organics to inorganics to microbiology, radiochemistry, where we have a lot of experience and we kind of have a long history is working with emerging contaminants. These are things like dioxins and PCBs that haven't really been emerging for a couple of decades now, to what we'd consider, I guess, now legacy emerging contaminants, things like nitrosamines and chrom-6 and perchlorate and that kind of stuff, or more recently, things like pharmaceuticals and personal care products. That was very popular on trend maybe 10 or 15 years ago, to more recently, PFAS has been kind of all over the news and unavoidable. And I know that I'm sure nobody needs a primer on PFAS, and everybody knows kind of what it is and what they are, but I figured I'd give a little bit of background just in case on these. These per and polyfluoroalkyl substances pretty much have been everywhere. Everybody's seen them in the news and in reports and these things that are persistent everywhere. They even have a big time Hollywood movie with the Incredible Hulk and Bill Pullman in it. This is a pretty big thing everywhere now. So these compounds are kind of very basic. It's usually an aliphatic backbone. They can be very short. Typically we see them down to C4 up to C18 or even heavier. They have an acidic functional group on one side, something like a carboxylic acid or sulfonic acid or something. And then on the aliphatic side, it's usually mostly or totally fluorinated. These compounds can have a little bit of different functional group. You could have some other esters or different things to change the chemistry around, but generally speaking, they look something like this. Now these compounds, because of the chemistry, that kind of unique environmental chemistry they have, make them a tricky compound to work with, right? These carbon-fluorine bonds are very, very strong, so this compound is very persistent. It's hard to break down with acid or heat or oils or different things. It's just very chemically stable. And because it's got that long nonpolar tail, they tend to be pretty lipophilic. So compounds that are both persistent and lipophilic generally in the environment tend to bioaccumulate. So the risk here, the thought is that perhaps, if somebody, say, irrigates a field with water that has been contaminated with PFAS, and that water gets into the food supply or it grows into the grass or whatever, and livestock could eat it, potentially the products that those livestock animals will generate, things like milk, other dairy products, eggs from chickens, could potentially have these compounds present in them because they could be lipophilic. So that's what we wanted to do and develop a method for these things. So these compounds are again very ubiquitous, right? And they're used for different things like fabric treatments, textile treatments, water repellent, stain repellent kind of stuff. They are used in performance chemicals, so AFFF, aqueous film forming foam for advanced firefighting, and other kind of industrial uses are very commonly we use these compounds. But what we've seen them a lot in is just regular household consumer goods. And this could be anything from food packaging to floor sealants to textiles. Even floss has this stuff. I mean, this is really super ubiquitous. And the risk here is that all of these consumer products that we use, things like old pizza boxes or microwave popcorn bags, that stuff just winds up in the landfill, and that could potentially leach out into the surrounding groundwater if you're not careful. So the routes of exposure, in my opinion, the greatest route of exposure for the average person is probably from food products, right? If you order a delicious pepperoni pizza from Domino's, it comes in that box that's pretty greasy up top, but it's not so greasy underneath. And the reason is because they generally are treated with some fluoropolymer that is a little bit of a grease barrier. So when you have that delicious slice of pizza, you're getting a little bit of pepperoni pizza and a little bit of PFAS from that grease that solubilizes that stain repellent or the grease repellent on the cardboard box. It could also be from environmental exposure, though. You could have things like industrial discharge or firefighting activities, or even, like I mentioned earlier, landfill leachate from just consumer goods accumulating in a landfill. All that stuff could kind of wind up in the environment and potentially give some exposure to people or livestock. I mean, if you're putting this water out for animals to drink or for growing feed for animals, there's potential for a route of exposure there by way of these products like dairy products and eggs from chickens. And there's some evidence to suggest that these compounds are probably not good for you. They're linked to some adverse health effects. It's probably better to avoid them if we can. So this compound, so PFOA especially, has been used a lot industrially. It's used as a surfactant. It's used as a kind of a intermediate in making Teflon products and other fluoropolymer products. And recently, a lot of these companies that manufacture these have undergone some regulatory pressures to try to eliminate these things. So they used substitutes, which are chemically not that different from PFOA, still have a lot of the same potential health effects and potential persistent nature in an environment. But things like Adana and Gen X are the two substitutes that have been kind of in the news recently because they're also being found in the environment, polluting waterways and groundwater, surface water, especially in North Carolina. I actually have a friend who's a professor in North Carolina working on a remediation for PFAS and try to figure out a way to remove this stuff from drinking water supplies and surface water and groundwater and that kind of stuff. So it really is an issue and it's a problem all over the place. So if we're looking at the target compounds that are in this target list that we've developed recently, we have a few fluorotelomere sulfonates. We have the classic carboxylic acids. We've got some sulfonic acids. We've got a couple sulfonamides. These are the derivatives that I mentioned earlier. We've got some sulfonamido ethanols, some acetic acids, and then of course the new PFOA replacement next generation kind of compounds. And in this list, we've got about 28 targets, I think. We've recently expanded our target list, so we're looking at some like 42 or 43 targets. And that's going to be something that I guess I'll give a little teaser that eventually we'll have a new application note with the rest of these targets on some other more streamlined approaches in food. So keep an eye out for that app note from Phenomenex coming out soon. So the sample prep that we use for these methods are, generally speaking, SPE, right? If we're doing a water sample, we use cartridge SPE, but really it only works for water samples. So kind of nicely flowing through an SPE cartridge. So we'll take a aliquot sample from a bottle, pass it through the cartridge, do the extraction generally on a weak anion exchanger, elute into a vial, concentrate it down, and send it for analysis. Now for food materials, for non-liquid samples, we decided on using catchers for this method because it was a little bit easy, kind of easy to work with in our workflow, and it was a streamlined method for us to develop. So when we're looking at different sorbents, we figured we'd start with something that we thought would be tricky, right? So we thought we'd use butter to screen different sorbents and see what works and what doesn't work. We actually ran into an issue though. We used the first studies we did was butter, kind of like this with that paper wrapping, and every single sample we tested had PFAS in it. We just couldn't find one that was clean. And it turns out the issue was not the butter, but the packaging. So we switched to the tub butter, and it was fine. We can get clean samples, clean matrix to do the testing. So just an example of how ubiquitous these compounds really are. So we tested a bunch of different sorbents and solvent combinations. So we used C18s versus SPE. We added some hexanes. We added PSA. The hexanes for degreasing, and try to evaluate what worked and what didn't work. And really, the best one that worked was just the PSA versus SPE without the hexanes. That gave us the best recoveries and the kind of most efficient matrix removal for this method, at least. And the prep we have was pretty generic, right? We took 1 gram of sample, added 10 mils of water, 10 mils of methane chloride, or not methane chloride, of acetonitrile rather, added 4 grams of mag sulfate, 1 gram of salt, shake it up, take an aliquot out, do the cleanup with mag sulfate and PSA, do the catchers, and take an aliquot, ready for analysis. Very straightforward, very easy, kind of minimal processing. And this was important because we didn't want to have to handle samples too much, right? The more you handle sample, the more you process sample, the more risk of contamination there is. So we wanted something that would be straightforward and relatively easy to do in our lab. So we had another issue where there were some requests that we got for looking at these compounds in eggs of seabirds, right? And these are going to be kind of tough samples to collect, very low volumes, and they wanted really low detection limits. So we figured we can kind of do a little extra cleanup to these samples to minimize the matrix effects and be able to hit a little bit lower reporting limits. I don't think the eggs we were using were puffin eggs. They were probably way less exciting, maybe seagulls or different things that were not as fun. But still, it was a challenge, and we figured we'd do something like this for it. So the idea here was that we would do catchers up front and then do a little bit of a conventional offline SPE cleanup. So we took a 1 gram sample to get 10 mils with the catchers, and then we took an aliquot of that final extract and cleaned it up with a wax SPE to get a final kind of cleaner extract after that. So what we did is we took our regular, kind of cleanup method, and at the end, took an aliquot. Instead of blowing it down for analysis, we took an aliquot of the final extract, diluted it up with water, and got it ready for SPE, and did SPE kind of in a conventional SPE fashion. So this was a kind of a small volume weak anion exchanger. We did the pH adjustments, kind of a regular SPE on it, diluted it out and concentrated it back down to 500 microliters. So we got no real concentration out of the SPE. It was mostly just for the cleanup. And this could kind of afford us a much cleaner extract. And the idea here is that with that cleaner extract, we can maybe mitigate the matrix effects a little bit and be able to hit a lower detection limit, a lower reporting limit. And we ended up getting an order of magnitude lower pretty reliably using this approach. So the analysis of these targets, it's a little bit tricky, right? There's some kind of unique challenges that we deal with when we're looking at PFAS analysis. First one is that you just got to go to really low levels. So you need a sensitive instrument. Everything we're looking at is in the parts per trillion pretty much level. So you need a lot of sensitivity out of this guy. You have to deal with kind of the relative polarities. You've got the C4s that are pretty polar, all the way to C8s or even longer, that are relatively nonpolar. So it's a bit of a challenge to make sure that your extraction is good, that the column has good performance for both polar and nonpolar compounds. So it's just an extra challenge. It's also an issue where a lot of these compounds, because of the way they're made, exist as either linear or branched isomers. So sometimes it's relevant to be able to resolve those, in an analytical standard. Maybe you just have the linear or the single branch, but in nature, you'll see the whole range depending on if they're weathered or not or how they're manufactured. So you'll see the straight chain isomer and a bunch of branched linear or branched nonlinear isomers in front of that peak. And the biggest issue I think that everybody has to deal with is contamination. So this is an example of one of the LCs in our lab, and all these green circles are spots where you could probably get leaching of some contamination, some Teflon bits in there, or different things that just could lead to background in the system. And this is really tough because these compounds are super ubiquitous. They're literally everywhere. Then they're in solvents, they're in the hardware in the LC, they're just everywhere pretty much. So there are a couple ways you can mitigate these background effects, right? The contamination. One is by swapping out all these Teflon bits with like PEEK fittings or stainless steel or different things that would not give contamination. Or you can put in a delay column in front of the injector to kind of hold up all that junk. So there's the two approaches. Both work. In our lab, we like to use the delay column. It's a little bit easier to maintain, easier to monitor. And when it gets too dirty, you can just regenerate or put it in the trash and get a new one. But I'm sure the column manufacturers also appreciate that. So looking at the low levels, one thing that I always mention when we're developing methods is that it's always important to pay attention to the modifier, especially if you're looking at kind of a lot of sensitivity. You want to make sure that that mobile phase modifier is appropriate for what you're doing. So in negative mode, typically we'll use like ammonium salts as a modifier, right? Because you want to generate that M-H ion. So things that people use are like ammonium acetate, ammonium formate. But one thing that I've been trying to push a lot lately, and I think people are using more and more, is ammonium fluoride. Ammonium fluoride, I think personally, is a secret sauce. I mean, it usually works great. You get a lot of performance out of it, and the reason is that F minus ion in the gas phase just rips protons off everything, so it'll deprotonate things that will just not want to be deprotonated. So it gives you better performance, get better signal in negative mode, generally speaking, but not in this case. In this case, because the targets we're looking at are already acids, they are already pretty much almost always deprotonated. You don't really need that extra boost of a modifier to help generate those negative ions. So you're looking at finding the right modifier that gives you the best chromatography and the best signal to noise. So in this case, we tested a couple different things and found that on this column choice, the best one was ammonium acetate. We got a lot more signal, pretty good chromatography, nice peak shape for all these guys. And this all happened, I don't know if you can see, but the run is about 4 minutes long, right? So the last peak comes out right at 3.9. So it's pretty good. We're very happy with the performance. It's, peaks are sharp, runs are short. It's kind of nice. So the column we chose was a Phenomenex Luna Omega PSC18, small particle column, 1.6 micron. We're doing either 2 or 20 microliter injection for these. Generally speaking, we try to go with a 2 micro injection to minimize the matrix effects. For some situations, we did experiment with 20 and it worked great. Again, you're putting more matrix on the system, so something to keep in mind. But the modifier we chose was ammonium acetate, and it worked great. Again, it's a 4-minute run, relatively high flow rate. The peaks were nice and sharp, lots of signal to noise, good resolution. So we were pretty happy with the performance of this column. And it seems to hold up pretty well, even though we're putting some kind of dirty things on it. Column seems to behave and tolerate it pretty well. So this is what a mid-level chromatogram looks like. Again, 4-minute run, pretty nice peaks across the board, pretty reasonable resolutions. I think it's 28 targets here. Plenty of signal to noise, so it's we're pretty happy. This is at 500 parts per trillion, and at the low level at 50 parts per trillion looks fine. And we have plenty of signal to noise. I'm sure we could go lower, but this was good enough for our applications. And again, the column works pretty well. And the one thing that I want to also mention is that issue with background, right? We use a delay column, so our background is very clean. Right?
How's it going?
Run just a solvent injection on the system, no IS, no anything, and we have no issues downstream. If we were to take out that guard column, yeah, we'd see peaks for a bunch of these targets, unfortunately, because that's just stuff that's in the solvent or in the system. But with a delay column, works great, and we have no issues with that. And we also have enough resolution to be able to resolve these branch to linear isomers. So these are 3 standards that we know that have a branch or linear, both the combo. So if that is something that's of interest, you can either slam them together or be able to resolve them and see what's actually in your sample, give a little more information to what you're testing. And on this instrument, we have tons of dynamic range. I mean, it'll calibrate many orders of magnitude, which is pretty nice. It's nice to work with this, especially if we're looking at an isotope dilution method where you really can't do a dilution on the extract if it is high. So having that big dynamic range makes it easy to work with. So the method works pretty well. All right, this is what the extracts look like up front. So you can see that they are kind of nasty, right? Butter's got a little bit of that butter layer in there. Egg's got plenty of color. The fish tissue's got chunks in it. So the extracts come out pretty clean. Even though it's got a little bit of color, they actually do come up pretty clean after cleanup. So the recoveries in milk are all pretty good. Again, this is a method that's isotope dilution. So we're spiking the IS into the sample up front, doing the extraction. The IS gets carried through the whole procedure, so it does a good job of correcting for any extraction inefficiencies or any losses, and for the matrix effects. And I'll show data at the end of the presentation of the difference between isotope dilution and external calibration. This is a little bit of a worse matrix at these levels, so it's it's not bad. It's still very good recoveries. We see a little more fluctuation, and butter also pretty good recoveries across the board. And the fish tissue is actually great. I mean, we got very little matrix problems from fish tissue. Processing whole fish is a bit of a different beast, right? If you're looking at whole fish, there's some other considerations. That's something we're working on for our next app notes. Again, a little teaser for you guys to keep an eye out for that one. But there are some other considerations to take into account if you're looking at the whole fish. But the tissue works fine. Now for cheese, again, a little bit bigger of a range, a little more fat in those samples, so a little bit more challenging to process, but again, recoveries are all really, really good for a lot of these targets. And doing the combination of the catchers and SPE, so this is a spike 10 times lower than the other samples, still really good recoveries in the egg. So we're very happy with the performance, and it works totally fine. And this is what I mentioned about the difference between an internal standard and external standard calibration. So this is a different set of data where we spiked milk samples through the whole extraction process. And these are the recoveries we'd expect if we're not doing correction with internal standards. So this is externally calibrated recoveries. Now, if you add the internal standard, so these are processed with the internal standard through the extraction, but not quantified with the internal standard. If you use the internal standard to quant, recurves get much tighter. Same with eggs. Looks kind of junky, kind of all over the place. We're getting some low recoveries for methyl fossa, but correcting for the IS, the drift is less bad. Same with the butter. Butter is more extreme. For two of these compounds that are generally poorly behaving, we get very low recoveries, but correcting with the IS, they come back to pretty tight recoveries, and everything's above 80%. Same with the fish, all much better with internal standards. So it's something that is important to keep in mind, that if the isotopically labeled analog is available, definitely should always use it if possible. So to kind of sum up these couple of methods, we have a pretty good method. It's only 4 minutes long. It works at the the trace levels needed for this kind of analysis, and it gives us really good performance. Good background contamination. Again, the key here is to remove the interferences or put something in place to minimize their effects. So we use a delay column, but you can use a delay column and removing the Teflon bits, or just remove the Teflon parts, but whatever it takes to get those samples to come out pretty clean on the instrument. So what you got to do. And with this column, such a small particle size, it's a really fast run, high flow rate, a lot of resolving power, so we have nice resolution with these different isomers. And the extraction procedure works great. I mean, it really handles a kind of a challenging matrix type. It's a bit nasty, especially for this type of compounds where you would see matrix losses and different effects, but handles pretty well for butter, milk, eggs, fish tissue. And then using that kind of two-step extraction procedure to get a little bit lower levels and a little bit cleaner extracts also works great, and we get really good recoveries. We're very happy about how these things work. And again, one thing that we're working on is kind of coming up with a little bit more streamlined approach, so a little bit easier on the extraction, and again, adding more target compounds. And we're looking at 42 or 43 target compounds, so it'll be in a future app note for anybody to keep an eye out for. And if you have any questions, I can answer them at the end of the presentation. Thank you.
Okay, thank you, Augustine. And we're going to turn the presentation over to Craig.
All right. So yeah, thanks everyone for joining us today. My presentation is going to look at low-level quantitation in water samples, introducing kind of two technologies that we have at SciEx. And what I'll be stressing is, of course, high sensitivity and precision, but also robustness. I am a staff application scientist at SciEx based in our Boston area lab. So just to summarize what I'll be covering today, in this case, those unfamiliar with these new technologies, the 6500 plus and the 7500 plus, these are nominal mass, triple quad, Q-trap enabled instruments. And with their introduction, they introduced some pretty significant technological advances that both increase sensitivity but maintain robustness. Because of course, for those trying to crank through large volumes of samples with good throughput, robustness, of course, is key. And what I'm going to be highlighting from the 6500 plus is the ion drive technology, which was able to increase sensitivity through improvements in the source, the QJet detector. And then what we used to say was our new instrument, but of course that's about a year old now, and is the 7500. And that was another leap in terms of technology, introducing the OptiFlow Pro source, the E-lens, and then the D-Jet. So of course I'll be covering these in more detail, but sort of keep those in mind because ultimately the question is, all right, you've got this fancy new box with increased sensitivity, but what happens kind of underneath the hood to improve that sensitivity? I'll be focusing in on PFAS and to show you that from moving from the 6500 plus to the 75, we were seeing signal to noise gains of about 2 to 9x for compounds, PFAS compounds. And this is important that I stress the signal to noise gains and not just raw signal, because of course, if you're enhancing everything, including the noise, then you don't really have any gains in your limits of quantitation. So again, I'll be kind of stressing everything as signal to noise gains. The way that we sort of were able to adjust the source parameters, the carboxylates showed the largest gain. And that's important because often their secondary transition is what's limiting us in terms of sensitivity. So Improved sensitivity is great, but what else does it mean? It means greater confidence in detection, of course, having those higher signal to noise values. And then as well, it's kind of the ability to see things that you couldn't see before. In this case, it may be the quantitation of PFAS isomers, but then also I'll show you some actual ambient water samples in which we could see some low-level, more hydrophobic PFAS carboxylates that I wouldn't have normally expected would be there. So anyway, that's just kind of a run through of what I'll be talking about today, and just kind of keep that in the back of your mind as I work through the presentation. So Augustine already did a great introduction. In fact, while he was talking, I took out some of my background slides as to avoid any kind of redundancy. But I always like to start off with this slide in nearly all of my PFAS presentations. And in fact, as a young graduate student at the University of Toronto, I remember reading these two papers that came out in 2001. In fact, the work by Giese and Kanan made the cover of Environmental Science and Technology. And here we are 20 years later, exactly 20 years later, and we're still worrying about PFAS, and there's still a lot of unanswered questions. And back in those days, Augustine was talking about adding, I think, up to 42 different compounds for some of his newer methods. Really back in those days, we were only worried about a small handful. The original human serum paper from Kristen Hansen at 3M really focused just on 3 PFAS. And of course, those lists have only continued to grow and grow. And Augustine mentioned the Gen X issue down in North Carolina. Some work from John Washington and science. Looking at some new PFAS as well from the Solvay factory up in New Jersey. So of course, we continue to discover new ones. I think the latest PFAS inventory estimated about 5,000 different PFAS compounds used in commerce, and we're only looking for a handful of those. And things obviously have evolved as our analytical ability improved. And I thought it was interesting that the early work looked at humans and wildlife in which levels had bioaccumulated or biomagnified up the food chain. Now we're able to go and look at ambient background water levels with low parts per trillion or even sub parts per trillion levels, which back in 2001 was really deemed impossible. Drinking water contamination is a big issue in terms of an exposure source. This map is biased obviously towards the United States, but clearly this is a global issue, and other countries are very aggressive with their monitoring and their regulation. The EU in particular recently has passed some pretty demanding regulations. So this figured, just from 2016. I think what's interesting about this is, it's really showing the PFAS contamination is kind of a series of small hotspots around the country. And because of that, that justifies more intensive monitoring, because, if we don't do a really spatially comprehensive monitoring program, then we clearly could miss some unknown hotspots. Of course, this map is kind of old now, at 5 years old, and no doubt it would be more colored in. And so just a couple things here. This is kind of nationally in terms of some of the regulations. Again, this is very incomplete. We could spend a lot of time talking about international guidelines, but even within the United States, some of the state-specific guidelines. Certainly some of the states have been more aggressive than the federal government. This here in February 2020 kind of died in terms of the proposed rulemaking, but certainly the latest UCMR5 seems to be that there will be some rulemaking that comes out of that. So that will be very interesting. But certainly drinking water contamination You know, it's not just from occupational exposure, it's not just from a downstream of a factory, but certainly seems to be kind of widely distributed. Okay, so you know, depending on the audience here and their experience with SciEx, you know, they may have started out their experience with SciEx instruments down in the early days. Certainly for me as a PhD student at the University of Toronto, you know, I first used a SciEx 4000. In this case, it was in the early 2000s. And you know, as we go along, we see these in some places, you know, kind of small steps in sensitivity, and then other cases quite sort of catastrophic increases in sensitivity. And so, again, last year, if I was presenting this, we would have just ended here at the 6500 triple quad. But of course, we now have the 75, which we'll need to update the graph for. But certainly, hopefully, I will show you by the end of the presentation that this is a you know, quite a substantial leap in terms of sensitivity. All right, so getting a little bit underneath the hood and kind of understanding, you know, what exactly is it in the instrumentation that's allowed us to get these sensitivity gains, and then I would also stress too, while maintaining robustness. So we're going to first talk about the 6500 plus. And so this introduced something called ion drive technology. And really what that was some substantial improvements in terms of the source, okay? So generating more ions. So the more gas phase ions you produce, obviously kind of the bigger you know, sensitivity potential you have. And then capturing those ions and transmitting them into you know, the Q1 region. That was improved, and then an improved detector. You know, in sensitivity as well as dynamic range. So this kind of nicely captures that. You know, when you generate more gas phase ions and you capture them and transmit them more efficiently and have an improved detector, then ultimately that will lead you down to improved sensitivity. And as I was always stress here, you know, you need to start looking at signal to noise gain, not just overall raw signal. Looking at the source a little bit more, you know, what was it able to achieve? And it's a little hard to see with this figure. You know, we kind of need an X-ray figure to look in here. But these are the heaters, you know, affectionately known as the hair dryers, blowing that hot air to try to desolvate those little droplets coming out of the probe. And so, you know, some of the improvements in there quite simply were to improve the diameter, you know, generating more heat, but also the geometry of those were optimized. And this figure, I think, kind of really nicely shows what it was able to achieve. And so if we look here in the top row, this would be the turbo V source that would be on kind of the 4000 or the 4500 or 5500. And then the bottom here is the ion drive source on the 6500. And then if we look, these are different temperature profiles, kind of looking down the source. And here with no temperature, 500 degrees and 750 degrees. And so the first thing to note here is, in fact, we are able to achieve hotter temperatures in the source for a given set point. And if we look at the highest temperature here on the far right-hand side, the other thing to note is that while the ion drive source may be a bit splotchy and a bit heterogeneous in terms of its temperature profile, with the 6500 ion drive source, we're seeing a much more uniform, homogeneous temperature profile. So not only is it getting hotter, but then you have a more uniform area, which is important for you, the user, because it means there's really more forgiveness in terms of the source and the probe position, because we have a much wider sweet spot. So more gas phase ion generation, typically due to the higher temperature, but then also kind of not as finicky in terms of the optimization for positioning. All right, then once those gas phase ions are produced and brought into the Q0 region, we've got the Q-jet here, which is just a better design in terms of capturing and transmitting those ions through to the Q1. And then finally, the detector, kind of more sensitive detector. It has a faster polarity switching, which generally for just doing a typical PFAS method of carboxylic and sulfonic acids isn't as important. But if you have a method that does have polarity switching, it's much faster, allows you to get longer dwell times. And then, a wider linear dynamic range, which is important when you're doing those injections of samples where you might have samples with both high and low concentrations, and that you don't want to do a dilution and re-inject. And then of course all of these instruments have our proprietary curtain plate and curtain gas designed to keep the instrument clean, keep out all the kind of uncharged neutrals, the dirty matrix that you don't want going into your instrument. So, again, we're able to achieve that sensitivity while maintaining robustness and high throughput. All right, so now we can look at the 7500 and what did it do to actually further advance us in terms of the technological gains that I just showed you from the 6500 plus. And here, very, I guess, similar in the fact that it is a Q-trap ready or Q-trap enabled instrument. Should you want to add that extra level of specificity to your analysis. And a slight difference too, it's run on a different platform, which is a kind of more powerful and more intuitive software platform. I won't get into those details at this point, but the fact is the power of the SciEx OS software to do your data processing and do a lot of those QA/QC calculations right in a results table that normally you would have to do in a third-party software like Excel really speeds up analysis. Okay, so again here I kind of stress the fact that should you want to use the Q-trap or enable it, it's something that can be done. Give you an extra level of sensitivity or selectivity if needed. All right, so I mentioned the Q-jet and its importance. The improvements in terms of capturing and transmitting ions, you can see here led to significant sensitivity gains. We talked about the 6500 plus, and compared to the 5500, we had about a 6-fold gain in sensitivity with that improved Q-jet. Now with our 7500, we have to use something called a D-jet. And the reason it's called a D-jet is that we're now focusing a wider beam of ions, and we have had to go to a set of 12 rods. So the 12 rods, dodeca, hence the name D-jet. And a lot of R&D was put into this to perform that focusing and transmission. I sort of alluded to it on the last slide, but parts of the improvements in terms of gaining sensitivity was capturing more ions, but also letting more ions into the instrument. So this would be, if you imagine looking down, from the source into the mass spec, this is your probe going down, and this darker blue dot represents the size of the orifice in the 6500, And then the orange here represents the size of the orifice in the 7500. So we're getting about a 4 times gain in area, which effectively means about a 4 times gain in terms of ions going into the instrument. Nice little kind of diagram here showing the plume of ions coming in and then the focus in by the D-jet. All right, so that's kind of the one improvement in terms of capturing a larger plume of ions. We have made improvements in the source. So you remember our Turbo V and then our ion drive on the 6500 Plus, and now we're moving to something called the OptiFlow Pro. Of course, again, we need really an X-ray image to see what's in there. And really the important technology in this is something called the E-lens. So this is a side view of the source, probe coming down and our droplet spray, and this being our curtain plate, and then to the right of it would be the D-jet region. So with the E-lens technology, we have this this rod here with an electronic charge that basically provides an electronic push of those gas phase ions into the curtain plate and into the orifice. So the estimate on that has been about a 2-fold gain in terms of sensitivity from using this E-lens technology, electronically forcing those gas phase ions in. And again, it's got that same high energy detector with great linear dynamic range and great LOQ for that. And of course, something I didn't stress specifically on here, but of course it's got the curtain plate to maintain robustness. All right, so those are the technological gains. I'm going to talk a little bit here just with the samples that we ran. Basic 10-minute gradient. In this case, we used the Phenomenex Gemini column. Augustine used the Phenomenex PSC18 column, the positive surface. We really like that technology as well. But both columns are fantastic columns for PFAS. And Augustine stressed the importance of those smaller polar compounds in terms of getting good peak shape and retention. And both the Phenomenex Gemini and the Phenomenex PSC18 do an excellent job at that. So pretty standard conditions here, of course, using ammonium acetate in the mobile phase. And the source and gas parameters were all optimized for both the 6500 and 7500. All right, so actually I kind of breezed through this quickly, but we have a low standard. This is a 50 parts per trillion standard, 1 microliter injection. And looking here at the comparison between the 6500 plus and the 7500. And just one thing I wanted to stress too is these were run on consecutive days, really wheeling the LC from one instrument to the other. So it is truly the best apples to apples comparison. And also I wanted to stress that here I've shown these source gas parameters and compound parameters are optimized for both instruments. So we were trying to get the best performance out of both of them. Again, something I've really kind of stressed throughout the presentation, we need to focus in on signal to noise, not just raw signal improvements. So what we did is we did a signal to noise calculation using the SciXOS software. And here I report the signal to noise for that low 50 ppt standard, 1 microliter, for both the 65 and the 7500, and then the ratio between them showing that gain in signal to noise between the two platforms. So here's a series of the sulfonic acids, as well as some of the amides and amide acids, and then some of the fluorotellumer sulfonates and some of the ethers. And so what we see here is we are seeing some gains in terms of sensitivity, 2 to 5, 7x gain in sensitivity. Again, showing an improvement from the 7500 versus the 6500. And then the way that we kind of focused and optimized the source conditions, we biased it so that we would show a greater enhancement in terms of our carboxylic acids. Because again, those that are familiar running them, typically the secondary transition for the carboxylic acids tends to be the least sensitive and kind of the limiting factor in terms of your LOQs. So, we set those source parameters to really emphasize their gains in sensitivity. And so you can see here with this series of carboxylic acids all the way from the C4 to C18, we're getting more dramatic improvements of sensitivity. Here really comfortably from kind of like 5 to 10x, depending on the compound. So let's look at some chromatograms. This is the butane sulfonic acid, and all of the slides I'm going to show you is the 6500 plus on the left and the 7500 on the right. And of course, we are seeing a pretty dramatic, kind of a tenfold gain in signal. But of course, the key is the signal to noise, and here we're seeing about a threefold gain in signal to noise between the 7500 and the 6500. For the hexane sulfonic acid, again, a larger increase. One thing to notice here, you can really see the improvements. You can see the noise isn't as well really variable as or noisy, leading to the improvements and also the gain in signal. PFOS as well. This one, the calculation isn't as high, mostly because I think this is really another set of clustered isomers here, branched isomers, that was impacting the noise calculation. But again, a dramatic improvement in terms of the signal. The C4 carboxylic acid, right, pretty substantial gain in signal to noise as well. That tends to be a tricky one, just more so from leaching because of from the LC components. And then PFOA as well. And actually here you can see the impact of using that delay column like what Augustine showed. So right about, in this case, just over a 13-fold gain in sensitivity. All right, so one thing I did want to stress, or I did kind of stress earlier, not only do you get gains in sensitivity, but these gains in sensitivity can often translate into you seeing things that you normally wouldn't see before. So, I mean, the 6500 plus is a phenomenally sensitive instrument. This is for the ethyl phosphoamide. And you can see here on the 7500, using that, we can now easily see these branch-chained isomers, right? And if you weren't aware of it, of course, when 3M made their PFAS through electrochemical fluorination, it was very violent and produced these branched isomers. Here with the 6500 plus, yes, you can see the linear isomer very well. Probably can't really see them here, and I would argue that that's noise. I certainly wouldn't feel comfortable standing up in front of an audience of my peers and saying that there are branched isomers there. But with the 7500, yes, very confident. Okay, just kind of to get into the last few data slides here. What else can increased sensitivity get you? Often it means better ion statistics, and better ion statistics often means better precision. And you can see that in the CV of the 5 replicate injections of this low standard. The CVs for the 7500 are in the rust bars, and you can see that all of those are much improved as compared to the 6500, and particularly for some of these lower sensitive secondary transitions here. So again, not just better sensitivity, but better data quality and better precision. All right, so we'll look at a couple, few compounds from a surface water sample. This is a naturally encouraged sample, not a spike sample. Again, what can the improved sensitivity give you? Means you can get better signal to noise, so more confidence. This again is the the C4 sulfonic. And then the other thing too is seeing these detecting these isomers in the water, right? So this is the sulfonamide acid. Here, those isomers look like noise to me. Hard to really justify quantifying those, but with the 7500, they are very easily seen. And I would say one of the biggest surprises for me from this data set was, in this case, a high order C13 carboxylic acid that I would not think would be soluble enough or polar enough to be in the water, in fact, was there. Here, this on a 6500 plus, this certainly would not pass your 10 to 1 signal to noise, but very comfortably seen in the 7500 and easily reportable from that. Okay, so just to sum up, hopefully I've demonstrated to you, what improvements we made in terms of the technology that resulted in this improved sensitivity while maintaining robustness, and then what else this improvement in sensitivity can get you, in addition to just raw signal gain. So with that, I'll finish up. Thank you very much.
Okay, thank you, Craig, for your presentation. Also, thank you, Augustine. As we said in the beginning, we'll open up questions. If you have any questions, type them in the chat box. There's a chat icon at the top right-hand side of your screen. So I will give everyone a couple of minutes to type those questions in. In the meantime, I will say that, again, this recording will be on the ACIL website. It should be there by the end of the day today. So if you'd like to review it again, please feel free to check out the ACIL website. So I'll give it just another couple minutes to see if we have any questions come in. Okay, it's not looking like, oh, we do have one. Okay, was sample solvent for injection when Wetchers plus SPE was used in 0.3% NH4OH in ACN? No issues with early eluting peaks? And I'm sorry, I probably butchered a lot of that.
No worries, I could take that. I mean, we were doing a small volume injection because we are injecting solvent. And we saw that obviously with a larger volume injection, like a 20 micro injection of acetonitrile, we'd need to get that, the initial conditions a little bit more aqueous to tighten up that first peak, or else it does tend to smear. But with the small volume injection, it wasn't too much of an issue.
Okay. Another question, is there a published method for the food PFAS?
There is not a published method. There's a new draft EPA method, 1633, that has a little bit of a streamlined prep for tissue, which I think could be adapted to food samples. But that's something that we're going to be working on and putting together an app note sometime soon for a kind of a more robust method that'll work for different types of samples, kind of based on that approach.
Okay. And did you do an internal isotope on your natural water sample?
Do we use a stable isotope standard for it? I think that was the question. Yes, we did.
Can liner ion trap feature further increase in the sensitivity?
Well, it can. In part, it depends on what's limiting your sensitivity. So using the ion trap often will get you an extra level of selectivity because you're monitoring the fragment of a fragment. And when you do that, you often reduce the background noise. So if you are background noise limited, then very much it can lower your LOQ values, particularly for dirty matrices. like some of those food samples that Augustine had mentioned, or soil samples and sludge samples as well.
Okay. And then there's a comment that the FDA has a PFAS method for food, US FDA C-010.01 method.
Yeah, I actually just looked at it. Thanks, Mike. There's a method, I guess, released a couple years ago for PFAS in food. So that'd be the reference for food.
And it looks like that is all the questions we have at this point. So with that, we will go ahead and conclude today's webinar. So thank you all for your participation. And again, thank you, Craig. Thank you, Augustine. And we look forward to everyone joining us on our next ACIL webinar.
Thanks so much, everyone.
Thank you.
Bye-bye.